On Monday, before we did our activity on Tuesday, we looked at two-dimensional interactions, collisions and explosions. And we saw that the law of conservation of momentum holds in both of those dimensions, not just pi equals pf, but rather pi equals pf for both the x and the y component. Now, yesterday we did an activity where we hopefully verify that law of conservation of momentum in two dimensions. But whether that works out for you or not, we still know deep down that we can use x and y, pi equals pf, for all of these problems involving objects moving on two planes, x plane and a y plane. We had a little bit of trouble with question number 2 because it involved a funny angle. And what's our problem with funny angles? We don't like them. We don't like funny angles. So what do we do every time we see a funny angle? We try to get rid of it. We do something to get rid of the funny angle. So what do we do first? Let's draw a picture, and then let's see where the funny angle appears, and then let's try to get rid of it in whatever way we get rid of it here. We got a 65.2 kilogram student on a 2.5 kilogram skateboard moving to the west. So here it is. We're going to call this object, I'm going to call it 1, 2, object 1 and 2 combined. Although it doesn't really matter. You don't even have to name it if you don't want to. Its mass is 67.7 kilograms. And its velocity is 0.40 meters per second. Now there's an explosion point, for lack of a better term. There's an explosion point right here where the person, the skateboarder, the student, goes down this way at 30 degrees south of west at a velocity of 0.38 meters per second. His mass is 65.2 kilograms. Where would we predict the skateboard would go? Well, we know it's going to go up, probably up and left. We'll find that out in a few minutes here. Its mass is 2.50 kilograms. All right. So you guys told me a minute ago that we don't like funny angles. We try to get rid of funny angles. So we do that by taking it off to the side. Before we worry about pi equals pf, x components, y components, or whatever, we just redraw this 30-degree angle. Because we don't like it, we want to get rid of it. This is x, this is y, this is 0.38. Now, the x side of this triangle is which side of the triangle? Opposite, adjacent, or hypotenuse? It's adjacent. So we're going to use the cosine function because it involves adjacent and hypotenuse. Cosine 30 degrees is equal to x adjacent over hypotenuse 0.38. X ends up being equal to 0.38 cos 30. What's that value? 3291? 0.3291. Thank you. Now we do the same thing for the y component except use sine. Sine 30 degrees is equal to opposite over hypotenuse. And the y component ends up being equal to 0.19 meters per second. There we go. Now, for me, you may not choose to do this, and that's okay. But for me, I like to erase this. Like, we got rid of the 0.38, right? So why do we want it sticking around there? Why do we want it in my drawing now? Let's erase it and replace it with 0.3291 and 0.19. I don't need the 0.38. I don't need the 30 degrees anymore because I've gotten rid of them. Still, I'll label this as object number 1 and the mass of 65.5 kilograms, 65.2 kilograms. Now, to me, this makes the problem a whole lot easier now. We don't have a funny angle that we have to deal with because we already dealt with it. Now it becomes a problem just like number 1 was, and just like all those other examples that we did. X components and Y components. Pi equals PF. I'm going to say M1 V1I plus what? Yep. 0. Why is it 0? Good. There's an X component. It is moving, right? No, it isn't moving, actually, is it? It's, what is it? Oh, wait a second. No, I've messed this up, actually. Right, this shouldn't be M1, V1I. They're together, aren't they? So we're going to say, I've made the mistake here, not you. we're going to say just MVI, right? Does that make sense? It's one object, right? Listen, if I make a mistake like that, like, stop me, call me on it, right? Okay, for the final, now we got two objects for the final, right? We've got M1 V1 final plus M2 V2 final. And total mass here is 67.7 times V1I is negative 0.4. Why is it negative? Connor, why is it negative there? The 0.4 meters per second before the collision takes place, or the explosion, I should say. Matt, why is that negative? Yeah, because west is, it's going to the west, right? It's going in the negative direction to the left. M1 here is 65.2 times, what's the value that we use here? V1F. V1F X component. Good. 0.329, but we're going to make it negative actually because it's to the left, right? Plus mass 2 is 2.5 times V2F. V2F is equal to, what is it? Negative 2.25. Okay, so the Y component, look, the Y component is pretty much the same thing. I mean, the way we do it is the same anyways, right? For the Y component, we say PI equals PF. We say, yeah.
PI is 0.
How come? Yeah, there is part of it moving horizontally. There's part of it not moving at all, but none of it's moving on the y-axis vertically. So the total initial momentum will be 0, equals M1 V1F plus M2 V2F. 65.2 times, what's object number 1 final y velocity? Stefan, you got that one? Yeah, good. We're going to make it negative, though, because it's going downwards, right? So negative 0.19. Plus 2.5 times V2F. We solve for V2F here. What does that work out to be? 4.2. Thank you. So now we combine them. Now we do our physics 20 work. 2.25 to the left. Sorry? I don't think it is. I think it's positive 4.27. Yeah. This goes over to the left side by adding, right? There we go. Solve for V. Hey, how do you solve for V there? Ian, how do you solve for V? Right. And how do you solve for theta? Maddie, how do you solve for theta there? Yeah, the inverse tan of opposite over adjacent. Good. When you solve for V, it works out to be 5.4. And when you solve for theta, that works out to be 66 degrees north of west. Had you drawn these the other way, 4.27 and then 2.75, it would have given you 34 degrees. No, 24 degrees west of north. Ethan, question? Who did he give me the right Boston? Okay, which one did he give me, X or Y? Did he give me Y? 4.9552. Thank you. 4.9552. Anybody else have that? I'd like you to take a look at a multiple choice question before we move further with another example of conservation momentum in 2 dimensions. This is kind of one. I just want to see what you can do with this and see if you can kind of maybe kind of think on your feet a little bit on this one. This is on about page 15 of your worksheet booklet, question number 23. Time to have a look here. This question says, at a coal mine, a train engine bumps an empty hopper car that has a mass of 10,000 kilograms. Really, the train engine is irrelevant here, right? The train engine gets this hopper car moving. The hopper car ends up moving at a constant speed of 2 meters per second under a coal storage bin, and then that coal storage bin releases the coal when its switch is tripped. So the coal comes down into the hopper car. We have a collision here, right? We have a hopper car going this way at 2 meters per second with a mass of 1.00 times 10 to the 4 kilograms. And we have coal going this way with a mass of 1.20 times 10 to the 4 kilograms. We don't know what its velocity is. How fast is the coal moving when it hits the hopper car? We're not really sure about that. Now, what happens when this coal hits the hopper car? This is a two-dimensional collision, right? The coal in the hopper car should go down this way, right? But there's a problem with that. The hopper car is on a track, and the track is on the earth. So in reality, although we would theoretically suggest that the coal would push the hopper car down and to the right, does it really go down and to the right? Kind of a leading trick question, because yeah, it does. It does go down and to the right, but not nearly as much as I have it drawn right here. The reality is, yeah, this hopper car and the coal do go down in addition to the right, but in order to go down when the earth is there, they have to push the earth along with it. So the entire earth goes down and to the right. Do you think the entire earth goes down very much? How come? Because what? Because of its mass, right? So listen, we're going to do the x component here of this, and then we'll take a look at the y component, and you'll see, if you haven't figured it already, why the y component, although it's technically there, doesn't really matter for this question, and doesn't really matter, in fact, for any question that involves the earth, where the earth becomes a part of the system. All right, so let's deal with the x component first here. Let's say PI equals PF. Let's say M1 V1I, that's a hopper car, M1 V1I, plus 0, because although there is coal moving, it's moving on the y-axis, equals MVF. M1 is 1 times 10 to the 4. That's 10,000 kilograms. V1I is 2 meters per second, equals the combined mass, which is 2.2 times 10 to the 4 times VF. VF, I believe, works out to be 0.909 meters per second. Is that right? Now, that's what lots of you got for the answer, right? Some of you probably said, okay, that's just it. I didn't bother doing X components and Y components. I just got 0.909. Well, the reality is if you got 0.909, you did do the X component. You just ignored completely the Y component and maybe didn't even give it any thought. How many people, when they got to this point, thought, well, there should be a Y component here, but I got the right answer. Like, what's the deal? Anybody give any thought to that Y component? There is a Y component here, but watch what happens. If we say PI equals EF, PF for the Y component, we would say 0, because the first one doesn't have a Y component, right? Just an X, plus M2 V2I equals MVF. Same thing, right? But what's M right here? Mass of the coal. What's M right here? Mass of the hopper car, mass of the coal, and the mass of the earth, because the earth gets pushed down with it. Now, because the mass of the earth is so big, we don't even know what V2I is, by the way, but whatever it is, doesn't matter. Because this mass is so big, VF is going to work out to be, I don't know, but really, really, really small. All right, try combining this and this in the Pythagorean theorem. What do you think you're going to end up getting? 0.909, right? See what I'm saying there? Technically, this is a two-dimensional collision, but because after the collision, we have the Earth as part of the system, it doesn't really matter. Okay? Do you feel the Earth shake a little bit if you're standing right beside this? Yeah, you probably do, actually. Okay, you probably do feel a little bit of a vibration, right? Okay. Does it take the Earth out of its orbit or change the orbit of the Earth? No, no, because it's such a ridiculously small velocity. All right. Good there? All right. I want to do one more example with you here. And then set you free on a couple more questions here, all right? For all the curlers here, we got a 19.6 kilogram curling stone, which is the standard mass of a curling stone, almost 50 pounds. Moving at 1.2 meters per second to the north, strikes another one off center. Okay, so let's start on this. Curling rock number one, 19.6 kilograms, and moving at 1.20 meters per second. Curling rock number two, same mass, 19.6 kilograms, at 0 meters per second. All right, there's the collision point. Now it says curling rock number one moves off east of north. So let's draw that up here. Number one goes east of north at 1.17 meters per second. And the mass of that, of course, is still 19.6 kilograms. The other object is going to go off over here somewhere. And listen, whether you're a curler or not, intuitively you know that if you would want to hit curling rock number two up and left, then curling rock number one is going to go up and right. If you ever played pool, it's the same thing, right? That's 19.6 kilograms, by the way. We want to find out what its velocity is. I'm going to put my pen down and you're going to answer my question. All of you are going to answer my question at once, in fact. What comes next? It was one of you. Ethan doesn't like funny angles. I don't like funny angles either. So what do we do with it, Ethan? Get rid of it. Let's take it off to the side over here and get rid of it. Let's put it out of its misery. Here's X. Here's Y. Here's 1.17. Here's 12.0 degrees. We're going to say this time sine 12.0 degrees is equal to X over 1.17. Sine this time, not cosine, because the X component is the opposite side of the triangle. This side of the room, Megan's side over, is going to calculate what X component is there. For the Y component, we're going to say cosine 12 degrees is equal to the adjacent side over the hypotenuse. Jack's side of the room is going to calculate the Y component there, 1.17 cosine 20. Let's go with the unrounded number here, guys. What do we get for the unrounded number there? 0.22432. Okay. Okay, that's good enough. The reality is you want essentially and theoretically an infinite number of significant figures there, unless it's a final answer. But the reality is, if you go 4 or 5, you're okay. But don't stop at two decimal places. Okay. What do we get for the Y component there? What did you get for the Y component there? Kenneth, what did you get for the Y component? 1.144. Let's keep going. Okay. Okay, that's good enough. So there's our X component, Y component. And what I like to do here, just so that we can visualize this, is redraw it so that we have an X now that is 0.24 3257, and a Y component that's 1.1443. So now, although I still have that red one that kind of looks like a funny angle, I don't know what that angle is, so I'm not going to worry about it. Let's change it up a little bit here. Say for the X component, PI equals PF. Tell me why PI is 0. Brendan, why is PI 0 there? Why is PI 0? No, well, that's right. I'm not analyzing the Y component. There is a Y component, but I'm analyzing the X, right? So good, good. There's two objects afterwards, M1 V1F plus M2 V2F. Oh, you spotted something. Make my life a little bit easier. Anybody else spot the same thing? Matt? Yeah, the mass is the same, right? For the first time, we get to cancel the masses. And that does make life quite a bit easier for us. So we say 0 is equal to V1F. Tell me what V1F is for the x component. John, what is it for the x component? Yeah, the green one, x. Yeah, yeah, 0.243257 plus V2F. So V2F for the x component equals negative 0.243257 meters per second. And then we do the y component. This time we have to say M1 V1I plus 0 because the second object isn't moving equals 2 objects afterwards. Masses cancel again. Same mass in every term. V1I is 1.20. V1F is 1.1443. What does that equal? 0.055, I think. Or 0.555, I think. Is that right? Figure that at 1.2 minus 1.1443. Now, you guys know what to do now, right? 0.24. Good. All right. Have a look at these ones, page 491.